So coming now to the introduction, a little bit about, let's say, IC fabrication. So you have two different main steps that are important. One, you have the device fabrication, which is the front end. All your transistors are located here below. And of course, if you want to send send signals from one to the other, you need interconnections. And this is the back end of line. These are interconnects that are connecting different levels of the chip to each other in order to transfer the signals from one place to the other. Now, of course, over the years, the number of transistors on an integrated circuit doubled every year. So that means that in order to keep up with this, say, speed, we need to also try to make the transistors smaller in order to make them faster. So the gate delay is decreasing when we go to smaller dimensions. However, the connections in between, they lose a lot of the speed because of what is called RC delay. And depending on the technology and the materials you use, you can see that this RC delay is going higher or lower. And there is a big need to characterize all new materials. Of course, once you go from one technology node to another one, you can introduce different materials. So you need to not only analyze them and characterize them, but you also need to do that at smaller scales. What is important, once you have processed a wafer and you have stacked many different dies on top of each other, you can do a packaging to protect the chip from the environment. However, when you do that, well, if you do simulations, for instance, you can find that the stress in the silicon chip after the processing is around 250 megapascal, which you can, let's say, compare to putting a car on top of your finger. So the stress you feel there is the same as this chip will feel. So it's quite high, and this makes inside this package the chip fail at some locations, and also this also will cause the ion shift, for instance, in the transistors to shift because of the stress. So most importantly, from a mechanical point of view, there can be cracks because of this chip package interaction, what they call. Now, of course, how to rank materials and to know how can we investigate this more. What we do is we have different test systems. This can either be a commercially available test chip or an in-house dedicated test chip. In-house means that we process our own levels and own technology. Commercially available is what different companies are doing, and of course this can be confidential, and we try to, of course, keep that confidentiality between imec and the company. And also thin film systems, it's more easy, it's more simplified. So that's also one thing that we are looking at, to simplify the more complicated test system. Then what we do is we want to, in the end, get finite element simulations of real devices in order to optimize and to see how they perform. So how to do that? We try to do experimental test methods. This includes, for instance, for adhesion 4-point bending or indentation-based fracture, elastic plastic properties by nano indentation, or shear microprobing, for instance. And once we have done these tests, we of course need to do some post-test analysis, meaning failure analysis, and also gather, of course, enough statistical information in order to couple it back to simulations, and then try to do an iterative process to see, okay, what can we improve? So the first part is like finite element modeling. So for those who are not familiar with that, you can compare it to different cases. So for instance, if you have a reality, you have this car here, and this farmer, what you do is you do a decretization into elements. Like if you would build it up with Lego blocks, and then you can give properties to each of these elements in order to simulate how this material or how this car, in this case, would behave if it would, for instance, hit a wall. You can do that for different, let's say, structures. I will not go into detail, but this is the basics. And of course, you need a lot of information there. You need geometry. For instance, here, if you see the SEM image compared to the simulation, you need, of course, the dimensions. You need material properties like Young's modulus, CTE, non-linear material properties like creep, plasticity. For instance, you also need loading conditions if you want to do mechanical simulations and some reliability models. So there are a lot of inputs, but most important, what we want to know is realistic input for these models in order to have a realistic estimation of the behavior of the real structure. Of course, experimental test methods. These are the equipments we have at imec. So we have two different Bruker systems, a TI Premier and a TI 950 Tribo indenter, and we also have a special stage, dual axis goniometer, where we can do an alignment between the probe and your sample to refine it. We have a 300mm chuck, a magnetic chuck, and also a heating stage. So for those who are not familiar with nano indentation, basically nano indentation, it uses a certain probe, typically diamond. Can also be different type of material, but most of the time it's diamond, and it's pressed inside the material. Then you record force displacement, and you do an analysis of the force displacement curve, and also you look to the imprints of the indents afterwards. You of course need to do some calibration of the probe, meaning you need to know what is the contact depth versus contact area of your material, and there are some equations which you can find, for instance, in the Oliver Farr analysis, what you can use. This is briefly for bulk materials. For thin films, it's more complex. There, I would refer to the ITF model for Bruker, where they can do substrate removal if you have a thin film, and we also apply that at imec at the moment. Pico indentation, that's also a system from Bruker. What we have is actually one interesting tool is that you also have an indenter system inside an SEM, and you can visualize fractures. You can visualize if you do a shear test like this on the bottom right. And this is very useful because people always like to see things before believing, of course. For looking to adhesion testing,